Let's step through writing our first data structure. So with this one, I have a bunch of stub functions and a class already written and a whole lot of code. It's on the student repository I have here, and it's right here. So when you download this, it'll have the Visual Studio project files and the CodeBlocks project files. So you'll just want to open that up if you're using one of these. And let's look at all of the different things, kind of what is available to us. So we have a smart fixed array here, and that's already defined, and we're going to be implementing the functionality that is not already implemented. And we'll talk about that in a moment, but I wanted to also point out some other things. So there are a lot of files in here, but some of them are for the unit tests, some of them are just utilities that you probably won't need, but I use in the unit tests and such. And then we have the data structures folder with our smart fixed array, a smart fixed array tester, so this is all of the unit tests for that. There's a bunch of custom exceptions we can use, and then there's kind of a really basic program. All it does is kind of randomly push and pop things from our structure, just as another way to test. When this is first run, you can choose to run tests or run the program. Either way, it won't crash, even though nothing is implemented. It'll run through the tests, and we can look at the results here, but this isn't all the information. But notice it'll say running the constructor test, that one happens to pass, running the shift left test, this one fails because it is not implemented, basically. And at the bottom we see some results and information about where to find all of the details. And if we run the program, we'll just see a bunch of exceptions happen because these functions are not implemented yet. So after you've run the tests, you'll need to go into your project file. No, not this one, it's the other right here. So wherever your code project is, your code blocks or your Visual Studio, there should be a smart fixed array test result that's generated. And when we open this in a web browser, it will show us more details. So the constructor passed here because the array size starts at 100 and the item count starts at 0. That is what's expected. And that's actually what was the case. So this one passed. And there's information over here on more, kind of things you could check if something goes wrong. Over here is more of a description of the test, what it's trying to do. And then as we scroll down, we'll see the rest of these tests are all failing because nothing is implemented. But as we start implementing them, we can run the tests again. If the functionality doesn't work correctly, we can go back and fix it and run the tests again. It'll tell you kind of what is expected for expected output and actual output, but we'll look at this more later once we are working on things. So I have a UML diagram here of our fixed array class, and we can also just look at the code over here. So with this smart fixed array, instead of having to implement storing data with an array and always having to rewrite, is the array full? What position does this data go to? And all of that, we're basically creating a data structure that gives us an interface to work with the data. So think of the data structure like you're going to be giving this data structure away for others to use, or you're going to use it in other projects. The idea is you don't want to have to re-implement the same functionality over and over. Implement it once, wrap it in a class, add the functions you need there and the error checking, and then you should be good to go. You could reuse this code anywhere. So we have functions to add data. So that's these push functions. Pushback, we'll put it at the end of the array. Push front, we'll put it at the beginning of the array. And then we have the insert at or push at function, as well as pop at and get at. So that's when we have a specific index we want to modify. The pop functions are for removing, so remove something from the end of the array, the front of the array, or at a specific index. And get just returns the data, whatever it is, at the back, at the front, or at a certain position. Then there are other functions that might be useful, such as searching for an item. So instead of passing in an index to get the data, we pass in the data and say, is this in the structure? And we return the index if it is. We also have display. We can output the contents of the structure out to the screen or to a different stream. We might want to get the size, how many items are stored in the structure, whether it's empty, whether it's full, and a function to quickly kind of erase everything. But we'll see that this is going to use lazy deletion. Then the way this is actually implemented, it's all wrapping this fixed length array, so the smart fixed array. It has whatever data type is passed in because it's a templated class. We have a constant array size, which is going to be initialized during the constructor time, and the amount of items that have been stored. So this will start off at 0, we'll have nothing in there, and as the person adds more items to the structure, this will go up. The shift left function is a helper function, which we'll see more of in a minute, and the shift right function is also another helper. So to start off with, some of these functions are already implemented, such as the constructor, which just initializes our constant array size, and calls clear, which down here sets item count to 0. The destructor isn't really necessary here, but I have it here because we'll also be working with a smart dynamic array, and that one will require more logic for all of our pointer management. So at the moment here, I just call clear. I don't have to do any sort of freeing memory because this is just a normal fixed length array. We don't have to do all of that micromanaging. So then as we keep scrolling down, we'll see more functions that are not implemented, and they have this throw not implemented exception here, and I have it marking what the function name is. So, anytime we run this, we can see smart fixed array size is not yet implemented, just as a reminder. So as we work through these, we'll get rid of those. A lot of people will comment them out. You can just erase them. They're not really needed. And then we can test one function at a time via the unit tests. So there are a bunch here. The top ones up here are probably the easiest. So we'll cover this functionality together. And then for the dynamic array, for that structure, a lot of the functionality will be similar, but there also will be differences. So I wanted to make sure we could step through this entire one together, get into how exactly everything works so I can explain things as we go. And then with the dynamic array, you can kind of figure more things out on your own. So the way this array is going to look is we'll have some fixed array. I'm just going to kind of draw a rectangle, and the array size is 100. I'm not going to draw that entire thing, but we'll have array size is 100. And then we have a variable m item count. And we have an array. So it already has all of the memory allocated, even if we're not storing any data in it. We'll just do that and pretend that this is the last item. So we have index 0, 1, 2, 3, 4, and 5, and all the way at the end, this is index 99. So when we start off, these will store garbage, most likely, unless the T templated data type has a constructor and initializes it. But we can pretty much assume none of this is in use. It might just store garbage, it could store default values, but whatever, none of these count as part of the data. So item count starts at 0. That means we have nothing is stored. And then as we go add more items, then we will increase the item count. So let's say we have Pushback, and we're storing maybe characters. So when we do that, Pushback will store this A, the very first item, at position 0. And then we have to increment item count. So that will then be 1. We can then call push back on B. Then B will go right here. And then item count will be added to again. And so on and so forth. So if we added a C, the C data would go at position 2 here. And actually the next place where you insert data, here or here or here, as you keep going, we're assuming we're not allowing any spaces, so no C here with a blank here, that wouldn't be allowed for the way we're designing this. The next index corresponds also to the item count. So when we have no items, we insert the first item at 0. When we have 1 item, we insert the next item at 1. When we have 2 items, just like this, we insert the next item at position 2. So we can use the item count to track where the next item or where the back of the list is. So over here would be the back, over here would be the front, and so we'll keep those in mind as well while we're implementing the different versions. Now another thing to look at is if the entire array was full. So let's say this is, I don't know, just $sign or something. How do we know if the array is full? Well, in that case, when we have 0 through 99 stored, we technically have 100 items. So item count is going to be 100. And in this case, when all of these spaces are taken up, item count and array size are the same value. So we know that the array is full if array size and item count are the same value. And remember, with our fixed length array, we can't resize those arrays. We can do that with dynamic arrays, but we aren't talking about that right now. So let's look at this code. With the size function, it returns an integer. As a user, we're expecting it to return how many items are stored in this array. We don't usually care about the array size in our other data structures in the future. We're not going to be bound by a maximum size, but for this fixed length array, we're doing that just as an example of how we could do some error checks. So in this case, what is the size? Well, that corresponds to the item count. So we just return the item count. Any error checks? Well, no, nothing could really go wrong. Item count is an integer. It could be 0. It could be a larger number. There's not really anything we need to think about as far as exceptions go. Down here, are we full? Again, the array is full if the array size and the item count are the same. So we can write return array size is equal to m item count. This is the shortest way we could write it. We could also say if m item count is array size. This can be in whatever order we want. We could return true or return false, but that's kind of redundant. This is asking a true-false question. If this question is true, then return true, or if this question is false, then return false. So instead, just like if we said bool result equals the result of this thing, this would be either true or false. We can also just return true or false by asking that question directly. Now for isEmpty, when we have nothing in the array, then item count is 0, and the first item is going to go to 0. So empty, item count is 0. We can say return m item count is equal to 0. And that's our condition for if the array is empty. Now display down here, I already have these implemented. This one could be useful to outputting the structured data to a text file if we needed to, or we could pass in cout directly, and we're doing that. This is an overloaded function. So we have display, it's given a output stream of some kind, and it just outputs the index of each item and the value of each element of that array. And it just iterates from 0 up until not including the item count. Because if we look at the array, and we have A and B stored at 0 and 1. In this case, item count is 2. So we don't want to include 2 because this would be the third item and it would be garbage or empty data. Okay. Shift left and shift right we'll come back to. These will be helper functions for when we are doing the insertion and the remove at specific indexes. But let's look at pushback. So remember with pushback, we just go to whatever the next available item is at the back of the list. So if C is here, then the back is now over there, and so on, and we can keep going. So what is the last item in the array? Well, again, that corresponds to the item count. In this current state here, item count is 2, so the next item gets stored at position 2. So we can say, if we're just not doing any error checks at this point, was it array? Yes, array at position item count is equal to the new item. Okay? But that's also not doing any error checks. What could possibly go wrong with a push? Well, if the array is full, if these are all taken, we can't put anything else into this array. So we could look for if it is null. This comment is old. Let me remove that because we're not doing a dynamic array here. We're not going to call resize. I need to update these comments, so I'll do that in a little bit. But in that case, if is full, then there's just no more space for any more data. And in some cases, we could just ignore it. We could just say if that, then that. If it's not full, do the do the insertion at the end and just ignore here. But if you were somebody using a data structure from someone else and there was some sort of error like this, like your array was full, but it didn't tell you anything about that, you'd be implementing a program and at some point it would become full, and then you'd get unexpected behavior, and you would be very confused because you don't see what's implemented in pushback, or generally a user of a data structure isn't going to see inside of it. So it wouldn't be good just to ignore this error, and actually it's better to make an exception and pass that to the caller. That way the caller can see, oh, there's no more space, I want to handle it this way, or maybe I want to do it an error log, or I just want to crash the program because now it's in a bad state. So we kind of defer how we're handling the error by using throw. So I'm going to go ahead and get rid of this else case. In the case where the array is full, we can throw, and I have these custom exceptions. So we'll say structure full exception. I wrote these exceptions so they take a function name and a message. So I like to just put the function name in here so we can kind of trace back where the error came from. And then we can say array is full as an error message. Okay. Now, when we did add this to the array, let's say this was 0 to begin with. Array at 0 equals the new item. Next time around, it should be adding it to 1, and then to 2, and then to 3. But at the moment, item count's not changing, so we need to make sure to increment that by 1. Now, if I had that commented out, if I forgot to add that in, we could still run these unit tests. So I wouldn't really read the results from that screen. I would go to our test result. Let's go ahead and refresh. Still didn't implement shift left and pop and all of that. Here's is full. The is full tests are passing. The is empty tests are passing. Push back, one of them works, where it is implemented, so that test passes. But this push test fails. And I need to fix some of these other things here too. So it tries to add 3 items and check that they're in the correct position. Here it's saying it's expecting 0 to be A, 1 to be B, and 2 to be C. but then the actual output, something is wrong. Item count is still 0. It did not add to item count. So we can use that as a hint for, hey, we're missing this part right here. Let's go ahead and run it again. Run tests and open that back up. And refresh, and then now my pushback function passes the tests. And we can also see item 0 is A, 1 is B, 2 is C. That's the actual output that occurred, and it matches the expected output. Item count is also the correct value. And for some reason I double outputted these, but that part's not a big deal. Okay. Now with the push front function, instead of pushing something to the end of the list, we're going to put it at the front. So let's say we have A and B here to start with. M item count is going to be 2. And let's say we say push front, and we're going to pass Z in. So then what that means is we're going to want to move these things over to make room for Z at this position. Well, how do we implement that? How do we move those over, and how do we make sure we don't just overwrite A with Z? Because if we say M array at position 0, which is always going to be the front, is equal to Z, well, that just overwrites this. That's not really what we want. We want to keep all of the data and just move things over. Well, that's what the shift right function will be for, that we're going to use and implement a little bit later. But just conceptually know that shift right, we can pass it a index of 0, and then this function's responsibility is to take B and move it over 1, and then take A and move it over 1. And then once this function's done, we have the array in this state, and then Z can go at position 0. So this one moves everything currently in there, this one adds it to the front. So in the code, even though we don't have shift right implemented yet, we'll still implement this, and the tests won't really pass. We'll come back around to it once we do shift right. So again, we're going to need the error check where we check if it's full, because if the array is full, there's no room for new things. Also, if we're going to say we want to move everything over, then we want to shift it to the right. However, if the array is already empty, we don't really care. We can just go ahead and put it at position 0 and increment the item count. But in that case, how do we know if we need to do the shift left or not, or the shift right or not? Well, if the size is greater than 0, we can ask that, or we could say if not empty. We can use either of these, but in that case, we're going to call the shift right function, and we're passing in index 0. So then it would be responsible for moving that stuff over, and then we're ready to put our new item at position 0. So that should be good. Okay, before we implement shift right, let's look at this last one down here for the inserts. Let's say we have this one, and we have an item count currently of 3, and we want to insert something at a given position. So we're going to say push at, and we're going to pass in, I don't know, R at, let's say, position 1. We're going to want to put it there. So in this case, again, we don't want to just overwrite this with R. We want to conserve that data that's still there. So that means we're going to have to shift everything over again. So that gets shifted right, but we're not shifting Z to the right because we don't want this whole thing to be shifted over. We're going to shift right, specifically starting at position 1. And then that should have the array in a state that we want ready for our new item. So shift is going to move those over, and then we can put the new item, our R, at the index passed in. So in this case, it's a 1. So then R would be here. Okay, so we're going to use shift right again, but from a specific index, whatever's passed in here as where we want to put the new item. Now for error checks, we would want to see if it is full again. That's going to cause a problem. Can't insert if it's full. But also, we can make our lives a little bit easier by saying, well, if they want to push at index 0, well, then they should have just called push front. We don't want to do all the extra work. They're just calling push front, might as well use that same thing. And then let's just return afterwards if they did that, because we don't need it to push twice on accident. Otherwise, if the index they passed in was the item count, well, then they were meant to do a pushback. And we'll just return that as well. So in that case, we're just reusing code we've already written, just calling those versions instead. And then in the last case, we're not full, so no errors, not putting at the front or the end. We're going to insert at a specific position. We need to call shift right at that index to make room for our new item, and then we call array at that index. We set that equal to our new item and increment the item count. So that's what we'll need to insert an item at an arbitrary spot in the array. Okay, now that we have these push functions, let's look at how shift right is going to work. And I have that one right here. So again, with an array, we have, for example, Z, R, A, B. Let's say we want to push from 0, or shift everything right from 0. Well, if we started at the left, and this would be implemented with a loop of some kind. Let's just say loop 0 to 3, because that's where each thing is at. Move I would be 0, 1, 2, 3 to I plus 1. That makes it's hard to tell if this is a T or a number. So if we implemented it this way, we'd start with 0 and we'd move 0 to I plus 1, which is 1. So we'd basically be overwriting R. Get rid of that. Now Z is overwritten R. And then we do that again, because then I is going to be 1. 1 will overwrite 2. So then Z is also going to overwrite 2. And technically these are just copied. They're not actually destroyed from their original location. And then once the item is 2, we're going to copy 2 to 3. And once it's 3, we're going to copy 3 to 4. So as you can tell, this is not the functionality we want. We don't want to go from left to right, because when we copy everything to the right, it's going to basically kind of corrupt our data. We don't want it to copy the same value over. So actually we need to approach this from the other direction. Instead of looping from 0 to 3, we're going to go from the end to the beginning. So let's say loop 3 to 0. So if we move 3 is the first I, 3 goes to 4, I plus 1. Then we go down to 2, 2 goes to 3. Then we go to 1, 1 goes to 2. Then we go to 0, 0 goes to 1. So in this case, we start at the end and have to go towards the beginning or whatever index was given to us. We move everything over by 1, and then we're good. Now something we'll have to consider as well is it's possible that we could have all of these spots taken up. So let's say we have everything up until 99. This is completely valid as an array. We have 0 through 99, so our M item count is 100. Basically, the array is full. So if we wanted to shift this over, we just wouldn't have room. Plus, we wouldn't have room anyway to add more items. So we'll still need to have our is it full check. Now, our other functions, these are already checking if it's full. We could also have it check if it's full here, or if we wanted to make sure this needs to validate that it will never, ever, ever be full when this is called, because something else has checked it, we could say assert, let's say not is full, and I need to include the assert. Or is it CAssert? Okay. So then in that case, we're saying that any functions that came before this should have already checked for this. We could also just copy paste this and have the same exception. It kind of depends on how we want to design this. This is okay, we can do that. So we're making sure that the array is not full. It should never be full when we call this. We can also say if the index is invalid. So if the index is less than 0, that's an invalid array index. Or if the index is greater than or equal to the item count, then that is out of bounds, because if we were inserting something, that would go right at item count. So if we haven't inserted anything yet, that is technically out of bounds of the array. So for instance, if we didn't have a full array here, item count would be 5, and so this is not a valid place to shift from. So in that case, we can throw another type of exception, like an invalid index exception, which is one of my custom exceptions that I have in here. I'm going to pass in the name of the function, and we can say index, and I have a handy little string library I wrote. We'll change this index to a string, is not valid. And so that could be another check. Or let's say, if I wanted to put this like this, we could do if that or if that, and check for either of those states. Okay, so once those error cases are handled, we'll say for int I is the item count, because when we shift everything over, this is the next valid place to go, so item count is fine. While I is greater than the index, I minus minus. We're going to go downwards from the back towards the front. So in each case, m array at position I is equal to the array at I minus 1. So that could also be, I wrote it like this, but we're essentially doing the same thing. If we're looping at 5, then grab 4 and put it over here. Same functionality, just a different way of writing it. And then that should shift to the right properly. So let's go ahead and run the test. And open the test file. So now push back looks okay, push front looks okay, and let's look for our shift. Shift right looks good. Here it expected A, B, C, D, and then we don't care what 1 was, but we shifted right at 1. So 0, 2, 3, 4 is 0, 2, 3, 4. That all looks good. We also checked if an exception occurred, if the array had a invalid index passed in, so that also passed. If we didn't have these error checks, like if I didn't have this here, that test would fail. So we refresh that test fails. So the unit tests also check for error states to make sure we're handling them properly. There. Okay, so we have the push functions taken care of. What about pop? So pop is how we're going to remove data from our array. So let's say we have just whatever this data is, our item count should be 5. and we want to remove from the front, or remove from the back, or remove from a specific index. So in that case, we have, let's start with pop back. It doesn't take any inputs because it's always going to work at the back of the list. So this is the back, this is the front. So if we call pop back, we essentially want to get rid of this thing. But what we're going to do is lazy delete. We're going to basically just say, item count is now 1 less. Let's say it's 4. So then we'd say these are the valid elements of the array. And when we go to push something at the back, such as, let's say, Q, then it says, oh, item count is 4. So the next index we insert at is 4. So Q is going to go here, and then that old data gets overwritten. So we don't actually have to clear out this part. We can just say that the array is now smaller, and we'll overwrite this data when we need to. This is known as lazy deletion. We're not actually like forcing the data to be removed. We're just kind of adjusting what we say is valid elements or indexes of the array and overwriting it later on when it needs to. So for the item count for pop back, we just say m item count minus minus. However, we still need to do some error checks. So if the array is empty, we don't want to do item count minus minus if nothing's in there. Then we'd get item count is -1, and that would cause problems. So again, we'll have a check. If the array is empty and they have called pop back, well, that's a problem. We can't remove from an empty array. So we'll just say throw, and again, I have a structure empty exception. And I'm going to put in the function here so we can kind of trace back what caused the problem. We can say array is empty. There we go. Cannot remove anything. That's a little bit more descriptive. Okay, so that's pop back. And, just as with everything else, we could maybe keep this over here, run this, run the tests, refresh. Now all of the pop back functionality works. Pop front, let's go ahead and just erase this and run the tests with that blank. Just to show that here's function not implemented when we refresh. It is implemented, so that passes, but now we have failing functions, and that's fine. That helps us figure out what we need to do. So with pop front, it added 3 things we can kind of determine here. And it was expecting item count to be 2 after pop front, but it was still 3, so this test failed. With this one checked for an error check for empty array. Just like up here, we checked to see if the array was empty before doing any sort of adjustments. We don't currently have error checks, so that one is failing too. Same error check as up here. Let's go ahead and run that again. Now the error check test passes because we're doing that, but we still aren't adjusting item count properly, and if we just did the same functionality, it would also fail because this is the pop back functionality. Okay. So now item count is correct, but it was expecting item 0 to be B and not A. So whatever it set up, it was, we could look at it if we wanted to, but it was adding some items and then they didn't get removed properly. So here is the actual test. You don't really need to go into the tests, but you can if you wanted to see what the values are. But it added 0, 1, and 2, A, B, and C. So we'll just copy that over here as well, so we can kind of see how this is all working. We had A, B, and C. And then we called pop front. So what that's supposed to do is get rid of this. But if we just simply remove that or set it to an empty character, that's not really doing anything. It leaves this blank spot. We don't want that. We actually want to move these back over, we're shifting left to overwrite that original data and also decrementing the item count. So it went from 3 items to like that. So we're going to need to make use of a shift left function, and we're going to decrement the item count. So over here, we're going to say shift left. And where are we shifting left from? Well, the very front. So over here, everything to its right, we're going to move these backwards. And we'll implement shift left it a little bit. So this test isn't going to pass until we do that. But that's how this is going to work. We'll shift left, we overwrite the very first item with the next item, and so on. And we decrement the item count. Okay. Now with the pop at function, this will be similar. So let's say we have pop at, and we want to remove the item at position 1 right here. So technically, we don't actually, again, remove that data. We just overwrite it. So we can shift left from the end of the array this way, and we replace the B with the C. So we just use a shift left again and adjust the item count. So the index here is where we're shifting from, subtract the item count, and then we can implement our shift left function. So with shift left, the way this one is going to work is, let's say we have these items. Well, let's add a few more items just so we can see. D and E. So if we want to shift left from 0, well, in that case, we're going to start here and say, okay, copy B and overwrite me. So then now that's B. Then we're going to go forward. Okay, copy C and overwrite me. So now that's C. Copy D and overwrite me. So now that's D, and then copy E, overwrite me with E. So we basically we can start at the beginning and move to the right-hand side and overwrite each item. So remember with shift right, we also checked for if the array is full and invalid index. We don't care if the array is full here because we're just shifting left. That means we'll have one fewer item used. So we do need to check if the index is invalid. So we'll do that here. Let's update this right here. If it's not invalid, then we're going to use a for loop, just like we do down here, except in the opposite direction. So for int I is equal to whatever index is passed in. I is less than the item count minus 1, I plus plus. And we do item count minus 1 because when we'd have 5 as the item count, so we don't want to stop there. We don't want to stop at 4. We want to stop at 3 because we're going to say, hey, grab 4 and move it to 3. We don't want to grab 5 and move it to 4. There would be no reason to do that. So here we'll say m array at position I is equal to m array I plus 1, copying the thing to its right, and then we should be good to go. Let's go ahead and run the tests. Okay, so now pop front looks good, pop at looks good, and I believe shift left is up here. Those all look good. And we still have our get functions not implemented and search. So let's go ahead and do those. So get back, the idea here is we have stuff. Back is going to be the end over here. And we just want get back to return whatever is stored there. So that's easy. We just say return whatever is in the array at what position? The very last valid position. Well, that's not going to be item count. Item count is where we would put the next item, so we'll do item count minus 1. So m item count minus 1. But we also need to do some error checking. If the array is empty, if there is nothing in here, well, we can't really return anything. If we did item count -1, that would give us a -1. That's not what we want. So let's copy the isEmpty error check. Throw that in there, and we'll go ahead and build and run. Let's check get back. That all looks good now. Okay, what about get front? Well, that's going to be the same thing, except it'll return the item at position 0. So this is the front. Return that item. Still need the isEmpty error check. Okay, go ahead and run and check the tests. There we go, those tests pass. And then also get at. So in this case, we need that isEmpty check, but we also need to make sure the index is valid. So I'm just going to scroll up here and look for one of these again. If the index is invalid, we do not want that. So get at. If it's invalid, we're going to throw that exception. Otherwise, we will pass back the element of the array at that index. Go ahead and run. Build. Now get at is passing. Okay, last is search. So for search, let's go ahead and just erase this. We need to return something, so let's just return -1 for now. But I just want to make sure our tests are running. So we have 2 tests. One sets up an array and looks for B. This one checks for something that isn't in the array. So how do we search for something in the array? Well, let's say we're looking for E. Well, we need a for loop. We start at 0. Is this E? Nope, nothing. Is this E? Is this E? Is this E? Is this E? Found a match. This is E, so return 4. Return the index. Otherwise, if we can't find it, if we basically check each item and we hit the end and nothing has shown up, then we're going to throw an exception because it's not in the array. So we'll do a for loop. For int I is 0, I is less than the item count, I++. If the item at this position is equal to what we're searching for, then we'll go ahead and return the index. However, we're not going to do an else case right here. This is a very common error, a very common logic error starting off. If we did that, we'd only look at item number 0 and either immediately return an index or something else. Not what we want. We only know that we can't find the item in the array, because it's not in the array, once we've searched everything. So we need to complete the entire for loop. And if we get down here and nothing has been returned yet, that means there's nothing there. It doesn't exist in the array. So let's go ahead and throw a item not found exception. And that's another one of these custom exceptions I made. We'll pass this one in here. We'll say item not found. Okay, let's go ahead and run. Run tests, exit. Refresh these. Now all of the tests pass. This is mismatched for some reason, but that's my fault. And so now our fixed length smart array is complete. This program here has a kind of, again, rudimentary program that just randomly adds and removes data. We can still run that. We can kind of watch it happen. It's just going to do that. It'll look at exceptions if they happen. It's not really going to affect the program. But it's just running through that. Here's the results at the end. It's all just random. But then if we wanted to actually implement a program and use this array to store the data inside of the program, we could just say, here's our M data, push data to the front or push data to the back. We just use it kind of like we would use our STL vector. And for the smart dynamic array, we're basically implementing our own vector, but that will be next time.